Quantum physics and atomic models. Quantum physics and atomic models will consist of the following subsections. First, electrons, X-rays, and radioactivity will be presented. Then, blackbody radiation and the photoelectric effect, which really set the groundwork for the quantum theory. Then various atomic models explaining how the atom is put together. Waves and particles, quantum mechanics, and then an optional section at the end about the various theories that are used to explain the atom, the nucleus, and the universe. Electrons, X-rays, and radioactivity. By the end of the 19th century, physicists felt pretty comfortable that they knew what was going on. Newtonian mechanics had been a while for several centuries and worked. Maxwell's equations had shown that electricity and magnetism were two sides of the same force, the same phenomena. Thermodynamics was integrated in with the energy theories. Thermodynamics is just another form of energy, like kinetic or potential energy. The speed of light was measured. And not was it only measured, but there was a theory that there was a stationary reference frame in the universe that everything was related to, and it was called the luminiferous ether. That was disproven, and that helped lead to Einstein's special theory of relativity in 1905. So as just said earlier, physicists were pretty comfortable that everything had been discovered and explained. But then new things started showing up, like the electron. A popular experiment was to take a tube of rarefied gas, that means gas that has a very tiny pressure near a vacuum, and the physicists would pass a current through the tube. The gas would glow, and this glow intensity would increase as the gas pressure decreased. As less gas was in the tube, there was more of a vacuum, the glow would get greater. These rays were emanating from the cathode, which is your negatively charged terminal, so they were named cathode rays, right over here. It was also shown that a magnetic field would change the direction of these rays. Now, if you'll remember from earlier on, a moving charge is affected by a magnetic field, and it was deflected in this case in such a way that these rays were proposed to have a negative charge. That's what they were measured. In 1897, J.J. Thomson found out that these cathode rays were actually discrete particles, which were then named electrons, again from the same Greek word that gave us electricity. He measured the mass-to-charge ratio, and he estimated that the mass of these particles was 1/1800th of a hydrogen atom. He also made the bold statement that all of these electrons were the same, independent of the material, the cathode in this case, that emitted them. Here's the tube that was used by J.J. Thomson, or rather a replica of it. It was called a Crookes tube, and in this case over here, in this section here, we don't have a magnetic field, but we have an electric field. And you can see when there's, we'll wait for it, positive on the top here, the electrons are deflected up here. When the positive is on the bottom, the electrons come this way. So that indicates that these electrons have a negative charge. The Crookes tube was good for determining the charge on the electron, but in order to find the charge to mass ratio, you need to use a mass spectrometer, and that was covered in the magnetism chapter. This is a replica of the third one used by J.J. Thomson. Now, once he had the charge to mass ratio, it was left to other people, Robert Millikan and Harvey Fletcher, who measured the charge. So, once you have the charge on the electron and you have a mass to charge ratio, you can then find the value of the mass of the electron. In this mass spectrometer here, electrons enter from over here. They come through an area where they are exposed to both a magnetic field and an electric field, and only electrons with a certain velocity will come out. They are then bent by a magnetic field, and determining where they hit the end or the sides of the machine, that gives you the radius of their circular motion, and you can then come up with the charge to mass ratio. Inside the mass spectrometer, you had a velocity selector where you could select the velocity of the electrons that you wanted to pass through it. You would do that by adjusting the magnetic field and the electric field so that their forces canceled out and you would have the electrons just go straight through. So we start with Newton's second law, F equals ma, and we have the magnetic force minus the electric force is equal to 0. The equation for the magnetic force is QVB. The electric force is QE. Do a little algebra here, and you wind up with, by setting E and B correctly, you can get a certain velocity to come out that was the ratio of E divided by B. The electrons with velocity equal to the electric field strength divided by the magnetic field strength then entered an area with only a magnetic field. This exerts a perpendicular force on a moving charge, so the electrons moved in a circle. The radius of this circular path was measured by observing where these electrons struck the sides of the tube. So if I start with sum of the forces ma is equal to ma, since this is circular motion, we use the centripetal acceleration v squared over r, and the only force we have acting now is the magnetic field. There's no electric field in this area. So once again we put in QVB for the magnetic force. It's equal to mv squared over r. We do a little algebraic manipulation here and we get charge divided by mass is velocity divided by b times r. And on the previous slide we showed that the velocity is E over b. We substitute that in and we get an expression here that the charge to mass ratio is the electric field strength divided by the magnetic field strength squared times r. We know what E and B are because those were set in the beginning. R was measured, so the calculation is carried out, and the charge to mass ratio for an electron is 1.76 times 10 to the 11th coulombs per kilogram. That now leads to the Millikan oil drop experiment. Robert Millikan and Harvey Fletcher, Harvey was the grad student, they determined the charge on an electron by using this experimental setup here. As you can see, it fits on a desktop. So once they find the charge on the electron, the mass will be found by using Thomson's determination of the charge to mass ratio. Here's a schematic of the oil drop experiment. Oil drops, over here, were sprayed into a container where they were charged by a very high potential source, several thousand volts. This electric potential was adjusted so that the drops fell with a constant velocity. So you'd have gravity pulling them down, and then keeping them up was the electric field. So this electric field was adjusted so this force, the electric field force, exactly balanced the gravitational force. So they fell with a constant velocity because the net force on the oil drops was 0, means 0 acceleration, so they're falling with a constant velocity. Since the observed falling times were all integral multiples of the smallest falling time, doing the math, Millikan and Fletcher came up with the statement, well, a couple things here. First of all, they found the charge on the electron, and they show that all charges are integral multiples of the electron charge. So that was a consequence of all the times being integral multiples of each other. As said a little bit earlier, the experiment was repeated many times with increasing accuracy, and today the accepted value of the elementary charge, which is the charge on the electron, which means there's nothing smaller than that, and any other charge has to be an integral multiple of that, is 1.602177, then of course there's other digits after that, times 10 to the minus 19th coulombs. Later on in this unit we will talk about an exception to this where there are some charges that are less than the charge on an electron.